All right, let's go back and share screen again then. Have to do this again. There we go. Yeah, thank you for reminding me of that. I was going to screw it up. Looks like this isn't working though. Let's see here. Excuse me, this is not working. Let me try it again. Let me do stop screen share. Hopefully we'll get this working in just a minute here. All right, let's try it again. Okay, I think that's got it. I think we're set up here. All right, can everybody see? Okay, here we go. So we're going to start tonight with a variational principle. There are very few quantum systems that are exactly solvable. So as a practical matter, we have to use resort to methods of approximation. Last semester, we studied bound state perturbation theory, which is useful when you have a system or a Hamiltonian that's close to a solvable system. And that can be used to find the energy eigenvalues and eigenfunctions of a Hamiltonian that's near a solvable system. Tonight, we're going to take up the variational principle, which is one of the answers to the question of what do you do if you don't have a nearby system that's solvable, which is common in practice, by the way. The variational principle is mainly useful for finding the ground state energy and ground state wave functions of various systems, or sometimes states that are near the ground state. Fortunately, there are many important applications where those are the precisely the states that one is most interested in. I mean, for example, in condensed matter problems, and typically one finds the Fermi temperature is much, much higher than the actual temperature. So you're dealing with low energy excitations above the Fermi sea and so on. So this is an example of where one is interested in things near the ground state. All right, so that's kind of a beginning to the variational principle. The variational principle is based on a simple theorem. It's almost deceptively simple. I'll begin with the theorem itself, and then I'll show you what it's good for. So let's suppose we have a Hamiltonian, and we got energy eigenstates psi and energies E psi like this, H psi equals E psi, and I'll put indices in on the energies and the eigenstates like this. And we'll assume the energies are ordered with E0 less than E1 less than E2 and so on like that. These energies are allowed to be degenerate, and in fact, at some point they may turn into a continuum. That's allowed in this setup. The theorem concerns what we call a trial wave function. I'll call phi as a trial wave function. Actually, the trial wave function, as far as the theorem is concerned, the trial wave function could be absolutely anything. What the theorem says is that if you take any wave function phi and you compute the expectation value of the energy, that this is greater than or equal to the ground state energy. In practice, the trial wave function is chosen to be something near the ground state wave function. One knows that it's near the ground state wave function, typically either by intuition or by some type of physical or numerical experimentation that tells you that. But the theorem applies to any phi whatsoever. In any case, this is the theorem. Let me prove it first, and then I'll show you what it's good for. So the proof works like this. Let me draw a picture in Hilbert space here, first of all. Let's say this is a sketch of Hilbert space. Let's say this axis is the ground state eigenspace. I'll call it E0, but it's allowed to be multidimensional because we won't allow degeneracies. And let's let the vertical axis be the subspace of the Hilbert space that's orthogonal to the ground state. Let's say that our wave function phi is some state vector that's sticking out here like that. If it's close to the ground state, most of its projection onto the ground state is actually the larger component of the two. So let's call that projection the ground state wave function 0 like this, multiplied by some factor, call it A. We have to multiply it by some factor because if phi is normalized, as we will assume, we'll assume this is normalized, then its projection will not be normalized. So we have to put in a scale factor like that to accommodate for that. And let's call the perpendicular part of the projection, let's call it epsilon. Epsilon doesn't have to be small because your guess might not be good. But if your guess was good, then epsilon would be small, and that's why I called it that. So in any case, what we've got is a decomposition of phi into a times 0, which is in the ground eigenspace, plus a part that's orthogonal to that, which we call epsilon. This means that epsilon's scalar product with 0 is equal to 0. These two are orthogonal to one another. Also, since phi is normalized, if we square phi, we get 1. But that's the square of the sum of these two terms, and the cross terms are going to vanish because of the orthogonality here. So this just becomes the absolute value of a squared plus epsilon scalar product with itself, like so. All right, that's the norm of phi. Now then, to prove the theorem, we consider phi sandwiched around the Hamiltonian. Because phi has two terms, this is going to give us 4 terms. The first one is, let's do it right. The first term is the coefficient a absolute value squared. A is allowed to be complex here. It's a squared multiplied by 0 sandwiched around h, plus cross terms. The first one is a times epsilon h0 scalar product, plus a star times 0 h epsilon, the matrix element. And then the last term is just epsilon h epsilon, that is to say state epsilon sandwiched around the Hamiltonian. Now, as far as the first term is concerned, the 0h0, the h acts on the eigenstate of itself, 0, and brings out the energy E0. And what's left over is the scalar product of 0 with itself, which is normalized. Since that's normalized, that just gives you 1. So this first term is the absolute value of a squared times E0. As far as the cross terms are concerned, the h acts on the 0 and again just brings out an E0. But that leaves behind the scalar product of epsilon times 0, and that vanishes because of the orthogonality. So this cross term goes away, and the other cross term also goes away. So so those middle terms go away, and there's finally the last term. As far as the last term is concerned, let me add and subtract E0 from the h, so we get one term that looks like this: epsilon sandwiched around h minus E0, and then a correction term, which is E0 is a C number, so I can bring it out. It becomes E0 multiplied times epsilon scalar product with itself. Now look at the first and the third terms. You see you've got a squared plus E0, you've got a squared plus epsilon scalar product, which is the normalization, that's equal to 1, times E0. So this whole thing, so we can rewrite this way, is that phi sandwiched around h is equal to E0. That takes care of the first and the third terms here, plus the correction term, which is epsilon sandwiched around h minus E0. Okay. Now, h minus E0 is a non-negative definite operator. What that means is that all of its eigenvalues are non-negative. That's to say they're 0 or positive. We know that because the E0 is just a constant, just shifts the eigenvalues of h down by E0, but the E0 is the first eigenvalue of h. So the eigenvalues of h minus E0 are 0, and then E1 minus E0, and then E2 minus E0, and so on like that, if you look at the eigenvalues of h minus E0. And you can see that all of these are either positive or else they're equal to 0, one or the other. So that proves, as I said, that h minus E0 is a non-negative definite operator. And that means that this correction term, therefore, is greater than or equal to 0. And that proves the theorem that the overall result, this expectation value, is greater than or equal to the ground state energy E0. Now, that's a pretty weak looking theorem, but there's a little bit extra that comes out of what we did, which is that the correction term here, as you can see, is quadratic in this correction epsilon. So if our guess to the ground state wave function was good, meaning that epsilon is small, what you can see is that the correction to the energy is actually second order in epsilon. So it might be better than you might think. In fact, this is typically how it works with the variational method, is that rather crude estimates of the ground state wave function can give you rather good estimates for the ground state energy. You just need to remember that the accuracy of the wave function is not as good as that of the energy. Now, there's a simple one-dimensional example which is worked out in the notes, which I won't go over here, but if you go through that, you'll see it's really quite interesting how good the answers come out with a kind of wild guess for a wave function. All right, so that's the basics of the theorem. That's as far as it goes. Now, what the theorem, of course, does is it gives us an upper bound to the ground state energy. You might think that's not very useful because just having an upper bound doesn't tell you how far away you are from the ground state energy. so you don't have any handle on the error. It'd be better if you had a lower bound as well, so you could bracket the ground state energy. And in fact, there are methods that can be used to find lower bounds as well as upper bounds, but they're considerably harder to use than the one that I've just described here. So I'm going to concentrate on just this upper bound, and we'll see, because as we'll see, it turns out in spite of these apparent drawbacks, it actually is quite useful in practice and gives us oftentimes very good physical results. Just having an upper bound, in other words. Now, in practice, the way we use this is not to have a single trial wave function, but to have a family of them. I'll call them psi now, and the family is characterized by some parameters, and I'll put a collection of states like this, by some parameters we call lambda, so that we call this a family of trial wave functions. And if we compute, according to the theorem, if we compute the expectation value of the Hamiltonian with respect to the trial wave functions, then the answer is greater than or equal to the ground state energy for all values of lambda. So what we would like to do is to search this family of trial wave functions to find the one that minimizes the ground state energy, because in a sense that's the one that gives us that's the one that is closest to the ground state. Now, to be honest about what we're doing is, if you want to say something is closest to the ground state wave function, you need to have a criterion or a metric to say how close is close. And in effect, what we're doing is we're just positing as a criterion the variational principle itself. The expectation value of the energy is the criterion. That doesn't necessarily work for the physical applications you might have in mind. For example, minimizing the energy might not minimize, let's say, a dipole matrix element, which is what you're really trying to calculate. So you need to keep that in mind in using the variational method. But in any case, this is the procedure which is typically followed, and it's oftentimes gives useful results. So what we'll say is that by the variational criterion, the best ground state wave function is the one out of the family that minimizes the expectation value. So here I'm assuming that these wave functions are normalized. I'll come back to a minute to what happens if they're not normalized. If I call this this function here f of lambda here is just define f of lambda, then f is an energy function depending on the parameter lambda. The lambda might be many parameters, might be a multivariable parameter like this, some collection of parameters like so. And if it is, then to repeat some elementary calculus in order to find the minimum, what you first need to do is to take the derivatives with respect to the parameters lambda I and set that equal to 0. And the points lambda naught where these derivatives are equal is really the gradient, if you will, of f you see in parameter space vanishes. These points lambda 0 that are obtained this way are called critical points of the function. That's the mathematical term for them. The critical point is not necessarily a minimum, it's just a candidate for a minimum. If you want to find out whether it's a minimum or not, one thing to do is to look for the second derivative matrix with respect to second derivatives of f evaluated at the critical point. And if this matrix is positive definite, then the critical point is actually a minimum. The reason being that if you make a small variation away from the critical point, then because this is positive definite, the value of f can only increase. If this matrix has all negative eigenvalues, then you're at a maximum, local maximum anyway. If this matrix has some eigenvalues that are positive and some that are negative, then you're at a saddle point. It's increasing in some directions and decreasing in others. And finally, if this matrix has some zero eigenvalues, then the test based on second derivatives is inconclusive, and you need to go to higher derivatives and do a more sophisticated test. But in any case, finding the critical points is the first step in finding the minima. So that's all standard stuff. Okay. Now, in practice, we sometimes it's not convenient to let me put it this way. In practice, sometimes we may have trial wave functions that are not normalized. If that's the case, then we can divide by the norm, like so, and that then just repeat the process, and that gives us what we want. Another alternative, however, if the set of trial wave functions is large enough, is that we just work with a subset of the trial wave functions which are normalized and forget about the rest. And we do that then by minimizing the function f under the constraint that the wave function be normalized. This can be done by using Lagrange multipliers. If I call the Lagrange multiplier beta, then I introduce a new function f like this, f of lambda beta, which is given by the following expression. It's psi of lambda sandwiched around the Hamiltonian. And then let's make it with a minus sign. Let's multiply by beta. And then we want the constraint function, which is going to be the norm squared of lambda, excuse me, of psi, minus 1 like this. So to use the Lagrange multiplier method, we introduce this function of now a collection of parameters, lambda. Now beta behaves like a new variational parameter. And we find critical points by taking df d lambda I and setting that equal to 0, but we also use partial of f with respect to beta is equal to 0. This latter condition, which I draw your attention to, just imposes the requirement that the wave function be normalized. So this is another possibility. Okay, now let me show you how this method using Lagrange multipliers can be used in a practical situation to get some useful information. Let's suppose I have a typical eigenvalue, eigenfunction, eigenvalue problem, h psi equals e psi. And let's suppose I've got some basis, which I'll denote by n, this collection of states, I'll denote by n like this. In practice, the basis which I'm introducing here is not the eigenbasis of the Hamiltonian, because normally you wouldn't know that if you're trying to use the variational method. Instead, you might be, let's say, for example, you might be trying to solve a one-dimensional problem with some potential that you can't solve, but the basis is the harmonic oscillator eigenbasis, which you know all about. So that's a typical way this might be used. Now we can take the unknown eigenfunction psi and we can expand it as a linear combination with some coefficient Cn of the basis functions like this, n equals 0. And if we go all the way to infinity, of course, we know expansion like that exists. The problem, however, is we don't know what the expansion coefficients are. On the other hand, if you're working on a computer and you have an infinite dimensional Hilbert space, which we normally do, then you can't represent an infinite expansion. You have to truncate this at some value. Let's make it n minus 1. So that we have, in effect, n total of n basis states that we're using, the lowest n basis states. Working on a computer, you practically have to do this. Now the question is, what are the expansion coefficients Cn? You get various approximations to the state psi by choosing different values of Cn. Let's choose the Cn, now using a variational idea, let's choose the Cn so that it minimizes the expectation value of the energy. Let's see what criterion that gives us for these coefficients. So here's what we're going to do. If we take the psi and form the sandwich around the Hamiltonian H and use this expansion, this can be represented then as a double sum on n and n goes from 0 to n minus 1 of Cn star, matrix element NHM, Cm like this. And likewise, psi scalar product, the square norm, is a sum on n equals 0 to n minus 1, or just the absolute value of Cn squared. And so if we use the variational criterion, we can introduce a function like this, which depends on the complex expansion coefficients, the collection of them Cn, and also on a Lagrange multiplier. And it's given by the following expression. It's a sum on n and m of Cn complex conjugate NHM Cm, and then minus beta times the sum on n of the coefficient squared Cn squared minus 1, like so. These are the matrix elements of the Hamiltonian, you see, with respect to the chosen basis. And the range on the indices gives us basically it's a truncated matrix. It's an n by n matrix now of matrix elements in the Hamiltonian with respect to the basis that we know. All right. So what we want to do then is to minimize f by varying these parameters. Now the parameters Cn are complex numbers, so we really want to vary the real and imaginary parts of each of the Cn separately. It turns out that in doing that, you get the same answer as if you vary Cn and Cn complex conjugate, Cn and Cn star, regarded as independent complex variables. It'll give you the same results. So let's do it that way. If I form the derivative partial of f with respect to Cn complex conjugate, what do I get? Well, you see it's going to remove the Cn from there. It's going to remove the n part of the sum. So I get the sum on m now of NHM, the matrix element, times C sub m. And then the Cn squared is, of course, the same thing as Cn times Cn star. So taking the derivative with respect to Cn star just cancels that. And so I get minus beta times Cn, and that's equal to 0. Likewise, if I take partial of f with respect to Cn, it turns out I just get the complex conjugate of the equation up above, which I'll write this way. minus beta Cn star, and that's equal to 0. And then if I take partial of f with respect to beta and I set that equal to 0, of course, that just gives me the constraint, which is sum on n of Cn squared is equal to 1. That's just the normalization. So these are the variational equations then that need to be solved for this particular minimization problem. Now, as I just mentioned, the middle equation, let me circle it here. The middle equation is actually the complex conjugate of the first equation. And so it has no extra information beyond what's present in the first equation. So I'm going to throw the middle equation away. As far as the first equation is concerned, what it tells you is that the expansion coefficient C sub m equals 1 to m0, excuse me, starts with 0 to n minus 1, are the eigenvectors of the truncated matrix of the Hamiltonian, truncated in there's an infinite basis, but it's been truncated to size capital N. And the C of m is an eigenvector of that with an eigenvalue beta. So that beta is the eigenvalue of this truncated Hamiltonian matrix. Beta, therefore, is an estimate, by just linear algebra. It's an estimate of the eigenvalues of the Hamiltonian.
Excuse me, I'm sorry. Maybe I missed it, but why have we truncated the matrix to size capital N?
Because we might be working on a computer and we can't extend it to infinity.
Oh, that's right.
So we're interested in finite representations of the wave function psi by finite linear combinations of our basis functions, because we're trying to approximate psi. Okay.
Yeah, thank you.
So this is what anybody would do in setting up a computer program and trying to diagonalize, find the eigenvalues of a quantum Hamiltonian. They would do it this way. However, embedding this in this theorem from the variational principle gives us a little bit of extra information. It tells us that the beta 0, that is to say the lowest eigenvalue, we can get the eigenvalues of this matrix and order them like this, like so, this eigenvalues of this matrix. It tells us that the beta 0, which is the lowest eigenvalue, is greater than or equal to the ground state energy. So we get a rigorous upper bound to the ground state energy by this procedure. Now, so it's a little bit of extra information. Now, actually, one can do better than this. There's what's called the Hilleras-Undheim theorem, H-Y-L-L-E-R-A-A-S, Undheim. Undheim. I can't speak and write, especially Swedish and German. I can't speak them and write them at the same time. It's the Hilleras-Undheim theorem, which says that if you have a variational trial wave function, which is a linear combination like we see here, I'll circle it here to draw your attention to it, then it turns out that not only is the smallest eigenvalue of the matrix greater than or equal to the lowest energy level of the real Hamiltonian, but the same thing actually applies for the other eigenvalues as well. For n goes from 0 up to n minus 1, like that. And actually, the Hilleras-Undheim theorem tells you more, which I'll let you read about it in the notes if you want to see about it. This is a special feature of trial wave functions that are linear combinations in the form that I just gave you a minute ago. More generally, the trial wave functions involve nonlinearities. And as a result, the set of trial wave functions as the parameters range over all the possible values, in general, is not a vector subspace of the Hilbert space, but rather some nonlinear, more complicated subset of the Hilbert space. But in any case, in this special case of linear parameters, it turns out that all the eigenvalues of the matrix are actually upper bounds to the corresponding real eigenvalues. Moreover, as the size of the matrix increases, all of these eigenvalues, beta, all the betas move down and become closer to the corresponding e's. Of course, as the size of the matrix increases, you get more betas too, because the matrix gets bigger. All right, so these are all features that come out of variations on the variational principle, no pun intended. All right, now, more generally, however, people frequently use trial wave functions that have nonlinear parameters in them. And if that's the case, then it's only the ground state wave function is bounded from above, and one cannot say anything about the other higher excited states. One gets no bound either above. One gets no bound, either a lower bound or an upper bound on the excited states. All right. So this is the use of Lagrange multipliers and linear combinations. let's see, here's something that we can say is that, let's go back now to general trial wave functions, psi of lambda here. Here's something that I should say is that if one has a set of trial wave functions, this is this type of thing that's commonly done in practice. You have a set of trial wave functions, then you do the minimization on a computer because you always have to in practice, and you get some answers. Now, something that's frequently done, almost always is done, is one then considers a larger class of trial wave functions, which includes the earlier set as a subset. You can do this by introducing more parameters, so that now the set of trial wave functions covers a larger part of the Hilbert space. If you do that, then you're guaranteed that the minimum eigenvalue will move downwards. It may not move downward at all, but it won't move upwards. You guarantee that it will not move up. Most of the time, it'll move downwards and thereby come closer to the ground state energy. You know that because the new set of trial wave functions, if it includes the smaller set as a subset, then the minimum in the larger set has got to be less than or equal to the minimum from the smaller set. So this gives one, numerically speaking anyway, a kind of a numerical experiment avenue to getting some sense about convergence. That's to say, you keep increasing the size of the set of parameters and watch how the energy decreases. Now, this is far from rigorous, but it's nevertheless what people do in practice, because oftentimes in practice one can't afford to be rigorous. And besides, it typically works pretty well too. All right, now, as I mentioned a moment ago, in the case of nonlinear parameters, one in general does not get either a lower bound or an upper bound on the excited states. It's only for the ground state. Nevertheless, there are circumstances in which one can get rigorous, at least upper bounds for excited state wave functions. Let me give you an example of where that can be done. It happens in systems with symmetry. Let's suppose, for example, we have a system that has parity as a symmetry, in which parity operator is pi. Then the Hilbert space E, as we know, breaks up into a direct sum of two subspaces that are even and odd under parity. The eigenvalues of parity are plus or minus 1. And if parity commutes with the Hamilton, the eigenvalues of parity are plus or minus 1, so the Hilbert space breaks up into states that are even and odd under parity. And if the Hamiltonian commutes with parity, as we'll assume, then basically it can be diagonalized on the even and odd subspaces independently. What that means is that if I take a trial wave function psi that belongs to the odd Hilbert space, then psi is automatically orthogonal to the ground state, because the ground state belongs to the even Hilbert space. So if you have a trial wave function which is rigorously orthogonal, we don't need to know what the ground state is to say this, you see. We just need to know that it has that symmetry. So if the trial wave function is rigorously orthogonal to the ground state, then it gives us the expectation value of psi gives us a rigorous upper bound of the first excited state. This is a variation on the variational theorem I proved at the beginning of this lecture, which is also easy to prove. More generally, another example of the same type of thing is you might have a central force problem in which the angular momentum is a good quantum number. So you've got L equals 1, 0, 2, and so on, different states like that, different angular momentum states. Effectively, each one of these corresponds to a different symmetry class. And one can use a variational method inside each of those symmetry classes in order to find the ground or upper bound to the ground state wave function inside each of those classes. So then you get a collection of rigorous upper bound estimates. Okay. That's not all there is to say about the variational principle. We're going to come back to it because it's quite important in many body theory, and you'll see it appearing again, and get an idea of how it's used in practice there. But that's all that I want to say about it for tonight. So are there any questions about this before I move on to another topic?
I had a quick question. How do we know that the minimum we're converging on is the global minimum and not a local minimum?
So the distinction between a global and local minimum is a distinction for these functions or functions of lambda that I'm coming up with. I mean, those are in general nonlinear functions. And you're quite right, they may usually do have more than one minimum. They got local and global minima. But the Hamiltonian only has one minimum eigenvalue. So all of the minima of that function f, all of them are upper bounds to the ground state of the Hamiltonian. And if you're using this method here and you have both local and global minima, well, you only find one global minimum. I mean, unless they're equal, okay, there could be more than one. But anyway, my point is that in minimizing this function f, you want to find the global minimum, because that's going to be that's going to give you the best estimate to the true ground state. Do you follow me? Now, when I change my function f to try to converge, it's a different function, and it may well have more local minima than the old one did. Again, I play the same game. I find the global minimum for each function f, and that's got to be enough. That's the best upper bound of what I've got at that level of approximation. Does that answer your question?
Yes, thank you.
Okay, good. Thank you for questions, by the way. I really appreciate them.
So the last part there, we're finding an upper bound for other states. Is that possible whenever you can break up your Hilbert space into orthogonal subspaces? If you take the wave function in one orthogonal space, then you can get.
No. It only works. It only works if those spaces are related to a symmetry of the Hamiltonians, because that makes the Hamiltonian block diagonal on the subspaces. You see, the Hamiltonian doesn't. Yeah. So that's why it normally works only with symmetry.
Okay, got it. Thank you.
If there was some way that God could give you a wave function that was rigorously orthogonal to the ground state without telling you what the ground state is, then you could use it to find an upper bound. But you don't have that, except by means of symmetry like this. You might say, let me choose a trial wave function that's orthogonal to the best trial wave function for the ground state that I've calculated so far. Would that work? The answer is no, that's not good enough. It's not good enough to have an estimate to the ground state. You've got to have something that's really, really orthogonal to it.
Okay.
Okay. The exception being when you have these linear parameters, then you have the Hiller-Sundheim theorem that gives you more detailed information about upper bounds. All right, then I shall now turn to the next topic, which is that of identical particles. There are a lot of particles in the universe, and most of them fall into a small number of identical classes because the number of particles greatly exceeds the number of different types of particles by a huge number. So what this means is that almost any quantum system one considers in the real world has identical particles in it. And it turns out that the quantum mechanics of identical particles are governed by a new postulate, new for us anyway. It's different from the measurement postulates that we took up last semester. It's called the symmetrization postulate, and it has a quite far-reaching impact on the physics of systems of many particles. In fact, it's indispensable for understanding the properties of bulk matter. And if you're going to do almost any kind of quantum physics, you'll be dealing with this all the time. So tonight I want to provide an introduction to the subject of identical particles, working through some examples. So for starters, let's write down, let's suppose we have two identical particles, and let's suppose, just for supposition, let's suppose they interact by means of a central force potential. So the Hamiltonian then is the kinetic energy of the two particles, P1 squared over 2m for particle 1, P2 squared over 2m for particle 2, plus a potential which we'll assume depends only on the distance between the particles, x1 minus x2, absolute value like this. This Hamiltonian describes a lot of physical situations. For example, if the two particles are electrons and the velocities are non-relativistic, then the interaction is primarily electrostatic, and this is a good approximation to describing the interaction of those electrons. Now, two electrons, of course, repel one another, and they don't have any bound states, but there is a scattering problem of two electrons. And if one studies the scattering of two electrons, one will find out that the symmetrization postulate about which I'll be speaking tonight has quite an important impact on for example, the form of the cross section for the scattering of two electrons. And hint, it's not a Rutherford cross section. It's a difference from the Rutherford cross section, and we'll come to that later on. However, for an introduction to the subject of identical particles, which is what I want to do tonight, I'd rather talk about bound states than scattering states. So let me not talk about electrons. Let me talk about something where the potential is identical particles, where the potential is attractive. One example of that is a case of diatomic molecules. Diatomic molecules, of course, have two atoms. And so the two atoms are going to be the two particles that appear in this Hamiltonian. They have to be identical to be talking about identical particles. So identical atoms means that the two nuclei are identical as nuclear species. That means that they're not only have the same charge, but they're the same isotopes as well. if we have a diatomic molecule with the same nuclear isotopes, it's called a homonuclear diatomic is a word for it. Whereas, and this would be, for example, ordinary H2, O2, N2, you know, the usual diatomic molecule Cl2 that occur, you know, in chemistry. On the other hand, if the nuclear species are different, then we have what we call heteronuclear diatomic molecules. And this includes, for example, carbon monoxide, hydrogen chloride, and there's a variety of them as well. So tonight we want to talk about the homonuclear ones. Actually, I'm going to exclude oxygen for reasons I'll explain in just a minute. Now, so we want to talk about a Hamiltonian describing two particles, which themselves are atoms. I have to say some things about what allows us to do that, because atoms, after all, are not they're not elementary particles. They're obviously composite particles. Hydrogen consists of a proton and a neutron, so it's at least two particles. Or if you want to count the quarks inside the proton, then it has three quarks plus one electrons, total of 4 particles. If you want to talk about nitrogen, you've got 7 electrons and 14 nucleons in the nucleus, so it's obviously a multi-particle system. So the Hamiltonian that I've written down here is really a model describing the interaction dynamics of composite particles. And there's a question of what justifies the use of that model. I may cover this later in the semester, it depends on what topics I decide to cover. But the name of the approximation that allows this or justifies this is the Born-Oppenheimer approximation. Born-Oppenheimer approximation is central to molecular physics and also to condensed matter physics, and it has applications in other areas as well. In any case, if we're talking about molecules, the conditions of validity of this Hamiltonian, this representation, are that the nuclear velocity should be small compared to the velocity of the electrons. And this is something that holds under normal conditions for most of these molecules. It's almost all low energy conditions this would hold. It's basically because the electrons are light and fly around quickly, and the nuclei are big and lumbering and move only slowly. All right. So under that approximation, this model comes out, and one has ways of ascribing a wave function to the composite particle. There is the question about the spin of the composite, mass and the spin of these composite particles. It turns out in the Born-Oppenheimer approximation that the mass of the particles is the same as the mass of the nucleus. The masses of the electrons are sort of hidden in the potential energies, it turns out. The spin of these atoms as composite particles is the same as the spin of the nucleus if the electron angular momentum can be ignored. The electron angular momentum can be ignored if the electronic wave function that we're talking about here, we probably want to talk about the ground state electronic wave function, has the quantum numbers known as one sigma in the language of molecular physics. I won't explain what that means. I'll just tell you that what these quantum numbers refer to are the spin and orbital angular momentum of the electrons as they move around the two nuclei. And basically, the singlet sigma means that electronic angular momentum is 0. And this applies to H2, N2, and Cl2. In fact, the most common homonuclear diatomic molecules. It does not, however, apply to the O2 molecule, which has the triplet pi electronic configuration, and that's why I'm excluding oxygen from this discussion. All right, so to summarize this and to make the long story short, we can use this Hamiltonian to a good approximation to describe the dynamics of molecules, treating the atoms as individual particles in which the spin of the atoms is the same as the nuclear spin. For the diatomics, most common homonuclear diatomics such as H2, N2, Cl2, and so on, but not O2. All right, now then, with that background, let me then proceed to talk about identical particles. By the way, the two masses that appear in these two kinetic energy terms are equal because the particles are assumed to be equal. Now, this Hamiltonian possesses a symmetry that we haven't seen before. It's exchange symmetry. I'll denote by E12, meaning exchange particles 1 and 2. I'll define it in just a moment, but it's easy to see by looking at this Hamiltonian that if I just swap the labels 1 and 2, that the Hamiltonian goes into itself. So when I do define this operator E12 properly, we'll find that it commutes with the Hamiltonian, and therefore there's a symmetry. And as we know, there's consequences of that. For example, the H and E12 possess simultaneous eigenstates. H does not connect states of opposite exchange symmetry, and so on. All these rules that follow from symmetry. Now, what is the definition of E12? Here's the basic idea. If I have a single particle Hilbert space, and let's say it's the space itself is given. We'll write down some set of basis vectors and write the Hilbert space as a span of those basis vectors. Let's label them by some index. Let me call it alpha, like this, for the single particle Hilbert space. Then for the two particle Hilbert space is spanned by products of basis vectors like this. For the first particle, alpha for the first particle is called a beta for the second particle, in which the indices alpha and beta run over the same indices because they're really labels of wave functions that are in two identical copies of the same Hilbert space. Let's write this for shorthand as just alpha beta, and this becomes the set of basis states for the product Hilbert space for the system of two particles. Then the operator E12 acts in the product Hilbert space, and the definition of it is given in this way. It's the definition of E12 is that it acts on alpha beta and maps it into beta alpha, just swaps the labels of the two states. Now, this only defines the action of E12 on a set of basis vectors, but by forming linear combinations, you can extend the definition to an arbitrary vector in the product Hilbert space. And moreover, one can show that the result is actually independent of the choice of basis in the single particle Hilbert space that we started with. So that E12, in a sense, is an intrinsic operator defined in the product Hilbert space. So that's the definition of E12. Now, so for example, if I take the case of two particles, let's say two spinless particles. Let's take the case of two spinless particles. Then we know that the Hilbert space for a single particle is spanned by the position basis kets that I write like this. Of course, there's a continuous index now. And so for the two particle Hilbert space, it's spanned by the basis kets x1 tensor product of x2, which I can abbreviate or define this to be x1, x2 like this. And if I do so, the two particle wave function, let's call it capital psi. I'll use capital letters for two particle wave functions as a function of x1 and x2. This is defined as the scalar product of the basis state x1, x2 with a state vector capital psi, like so, definition of a wave function, like so. And what this exchange operator will do in this case is it'll act on the basis state x1 and x2 and just swap the two positions, x1 and x2. And so this makes it pretty clear, I think, and it's easy to show in detail, that under exchange, this wave function, E12, will get mapped into a wave function in which the coordinates are swapped. X1, x2 goes to x2, x1. All right. If we have wave functions with particles with spin, it's only slightly more complicated. In this case, for a single particle, the basis states are the tensor product of x with m, where m is the magnetic quantum number of the operator S of z of the particle, so that m takes on the values going from minus s up to plus s, like this, and we'll abbreviate this as just xm, like so. Then for the two particle system, the basis states can be written this way as x1, x2, m1, m2, which is a tensor product of x1, m1 with x2, m2. Basis states for the individual particles, like so. And then the wave function now has capital psi has four indices, m1, m2, and x1, x2. And you can see what exchange does to it. It's going to map it into psi of m2, m1, and x2, x1. So both the spin coordinates and the spatial coordinates are swapped by means of this operator. So this is the official definition of the exchange operator in these various, given in general up above, but now illustrated in these various cases for particles both with and without spin. All right. Now from these definitions, it's clear, first of all, that E1 squared is equal to 1, so it squares to unity. It should also be clear that E1 is unitary because it preserves the norm of the wave function. That's the main reason. Also, it's invertible. It preserves the norm of all wave functions. So E12 dagger is equal to E12 inverse. And E12 inverse is equal to E12 since E12 squared is equal to 1. So what this means is the exchange operator here, exchanging these two particles, is an operator that's both Hermitian and unitary. All right, and as I explained above, this E12 commutes with the Hamiltonian. The Hamiltonian I wrote down above anyway commutes with that one. So this means then that the Hamiltonian possesses simultaneous eigenstates with the exchange operator E12. Now, what I'd like to do now is to go back to the specific example of the diatomic molecule and go through in some detail to show you explicitly how it is that basically we'll work out what the energy eigenfunctions are, and then we'll show that they are or they can be organized in order to be also simultaneously eigenfunctions of exchange. Let's see how that works out. So to begin with, I'd like to talk about a diatomic molecule in which the atoms are spinless. That means the nucleus is spinless. And so for that purpose, I'm going to choose the carbon-12 nucleus, carbon-12 nucleus. Carbon-12 nucleus has a spin of 0. It's a spin 0 boson, spinless particle. And so I want to talk about the diatomic molecule, which is the C2 molecule. Like so, it's really C2 with carbon-12. That's what we want. Okay, so let's see. Let's talk about this molecule. So the Hamiltonian, to go back to it, here it is a central force problem. And we know how to analyze these problems like this. We need to go to a center of mass coordinates and relative coordinates. We did this last semester. In fact, the problem is a little bit easier now than it was last semester because the two particles being identical have identical masses. So this simplifies the transformation. So let's write down the transformation then. The center of mass R is given by the positions of the two particles x1 and x2 divided by 2 because the masses are equal. The relative position is given by x2 minus x1. Let's write it that way in that order. The conjugate momentum to the center of mass capital P is the total momentum P1 plus P2. And the relative momentum lowercase p is equal to P2 minus P1 divided by 2. And this is a canonical transformation of the variables of the system. And when we transform the Hamiltonian, which was originally P1 squared over 2m plus P2 squared over 2m plus v of the distance between the particles, becomes equal to capital P squared over twice capital M plus lowercase p squared over 2 mu plus v of r, where capital M is the total mass, which is twice the mass of the individual particles, and lowercase mu, which is the reduced mass, is m over 2, like so. This is just a special case of what we did last semester, so I'm omitting the algebra. This is, of course, the sum of the center of mass Hamiltonian plus the relative Hamiltonian. Again, we went over that last semester. As far as the wave function is concerned, let's call it capital psi. It depends on the coordinates of the two atoms, x1 and x2. Let's transform the coordinates over to center of mass and relative coordinates, and we'll use the same symbol for the wave function, like this, r and r, like so, meaning the value is the same. The function is different, but I'll use the same symbol for it. It's psi of r, small r, and capital R. If we want capital psi to be an energy eigenfunction of H, then eigenfunctions exist in factored form because the Schrodinger equation is separable. In fact, we can write this as capital phi of capital R multiplied times some lowercase psi of lowercase r, like so, in which capital phi is an eigenfunction of the center of mass Hamiltonian, which is just a free particle, as you can see, and lowercase psi is an eigenfunction of the relative Hamiltonian, which is a one body central force problem, again, just like we did last semester. So as a result, we know some things about this. We know that capital phi of r is a free particle eigenfunction. It might, for example, be a momentum eigenstate, e to the IP dot r. That'd be a simple choice, certainly. And we know that the relative wave function psi of r, it can be chosen as an energy eigenfunction. It's being a central force eigenfunction. We can write it in terms of central force eigen quantum numbers NL and M of r theta and phi, which is a radial wave function r and L of r times the YLM of theta and phi, again, following what we did last semester for central force problems. So we know we can do this. Eigenfunctions exist that look like that. Allow me to write this in Ket language in the following way. Let's write capital psi is equal to capital phi, which is the center of mass wave function here, multiplied times lowercase psi, like so, which is the relative wave function. And I'll also write this as capital phi times NLM, giving the quantum numbers of the relative wave function. Let's write it like that in Ket language. And if we do, then this is an energy eigenfunction, so that H on capital psi is equal to what? It's equal to the energy of this state. But there's two energy terms that come out. There's a center of mass energy from one term and the relative energy from the other term. So it turns into this. It's capital P squared over 2m. That's the kinetic energy of the center of mass motion from the center of mass part. And then the relative motion gives us an E sub NL, which is the energy eigenvalues of the relative motion times capital psi, like so. All right. So these are the energy eigenstates. Now, I want to examine what the exchange operator does to these energy eigenstates. Let me go ahead and do. I'm debating which of the two topics to deliver first. I'll tell you what. Before we talk about the exchange operator acting on this, let me make a digression into a little more detail into what the E sub NL looks like and what the wave functions look like. This is something of a repeat of some material from last semester, but I'm going to give it to you anyway because I think it gives you a more vivid picture of what we're doing if we have a fairly concrete idea of what these energy eigenfunctions actually look like. So let me say some things about that, about what these E sub NLs are. So to do that, I begin by sketching the potential energy for the diatomic as a function of radius r, v of r. This is the v of r which appears in the center of mass Hamiltonian, in the relative Hamiltonian, which is up here. It's a central force Hamiltonian. I described this last semester. It's a potential that looks something like this. It's a well. It's repulsive at short distance. It's weakly attractive at large distances. It has a parameter here, well depth. Let's call it minus v0, and a radius r0 to the range of the well. These are just crude parameters of this well. This well supports vibrational bound states, which are energy eigenstates down at the bottom of the well. And we get some crude sense of those energy eigenstates by making an approximation on the potential near the bottom of the well. It's minus V naught, which is the depth of the well. And then if I introduce a harmonic or quadratic approximation to the potential there, I can write the rest of the potential as 1/2. It's the reduced mass M times the vibrational energy V vibrational squared times R minus R naught squared, quantity like that. And then there's a centrifugal potential as well. Excuse me, there's a centrifugal potential as well, which I'll include in V here. And that's H bar squared times L plus 1 divided by 2 mu R squared, like so. All right. Now, if we're near, again, I'm repeating myself from last semester, if we're near the ground state, in the ground vibrational state, then the ground vibrational state wave function is rather narrow. It occupies only a small fraction of the range from 0 to R naught. About 10% is a rough estimate for typical diatomics. And that means that over the extent of the wave function, the radial variable that occurs in the centrifugal potential is almost equal to the value R naught. And so let's make an approximation by replacing that by R squared by R naught squared. And if we do this extra term, then just becomes a constant. Physically, this extra term, the centrifugal potential, is the rotational kinetic energy. And in fact, it turns into, as you can see, it's an L squared over twice the moment of inertia. It's what you get for the rotational kinetic energy of a rigid rotor. In any case, what this means is the energy eigenvalues E sub NL are approximately given by the energy of the harmonic oscillator, which is N plus 1/2 H bar omega vibrational, and then plus the rotational energy, which is H bar squared L times L plus 1 over 2 mu R naught squared. This is kind of crude estimate for the energy levels. But I'm giving it to you anyway, as I say, just to give you a concrete idea of what these energy levels look like and to give you an idea of what we're talking about when I write these E sub NLs up here. All right, but in any case, this is how this works out. Now then, so these are the energy eigenfunctions of this diatomic molecule, in this case, the C2, the carbon 2 molecule. Now, to go back to exchange, what does exchange do to the state psi? Here, let me repeat what the state psi is. It's back here. Here's the state psi. It's a product of the free particle center of mass state plus the NLM for the relative motion. Let's look at what E12 does to various operators. Let's look, for example, at the center of mass operator. What does E12 do to it? Well, if I go back to the definition here, you can see that swapping coordinates 1 and 2 doesn't do anything to the center of mass. It's invariant under exchange. Whereas the relative position vector, swapping 1 and 2 changes the sign of that. So we have these rules as the capital R goes into capital R under exchange, whereas lowercase r goes into minus itself. And this tells us that E12 acting on a wave function psi, or let me put it this way. Let me write it this way. If I have the wave function psi of capital R and lowercase r, and I apply the exchange operator to that, this is going to go into psi of capital R and minus lowercase r. Okay. So this is the behavior of exchange on the wave function of a two-particle system consisting of identical particles. You see that exchange, excuse me, you can see that exchange has the same effect as parity insofar as the relative motion is concerned, but not insofar as the center of mass is concerned. The parity operator would flip the sign of both of these, big R and small r. Exchange does only one of them. As a result of this, it's easy to confuse exchange with parity. And I advise you not to do that. People that back in the days when we had oral prelims, which we don't have anymore, you should thank yourself. Thank somebody for that. Thank the lazy professors who didn't want to do it anymore. That's what you should do. But anyway, in the old days when we had oral prelims, the students always got tripped up because they confused parity with exchange. But anyway, they're quite different physically and have quite different consequences. Nevertheless, mathematically speaking, exchange, as far as the relative variable is concerned, does the same thing as parity. And we know what parity does to central force eigenfunctions. It brings out a phase factor of -1 to the L. That's the parity of those eigenstates. That's all we're talking about in the relative motion. And therefore, if we let exchange act on this wave function, it's not going to do anything to the center of mass wave function because it doesn't change R at all. But what it's going to do to the NLM wave function is it's going to multiply it by a -1 to the L. That comes from the YLMs, if you'll recall. So what we have here, if here's what the Hamiltonian does to psi, what does exchange do to psi? The exchange acting on psi is going to be E12. It's going to be exchange acting on the phi part times the NLM part. And this doesn't do anything to the phi part, but it brings out -1 to the L from the other part. So this turns into -1 to the L times psi. And so what we see is that the promise that was there, since the exchange operator commuted with the Hamiltonian, we knew that there had to be simultaneous eigenstates. That promise is fulfilled because these eigenstates that we just worked out just by working with the Hamiltonian alone turn out to be automatically eigenstates of exchange. And the eigenvalue is -1 to the L. They're either even or odd, depending on whether the orbital angular momentum of the relative motion is even or odd. So that's an important conclusion. Okay, so this is an analysis then of a Hamiltonian with a simple symmetry. There's two symmetry classes, and they're even or odd. And we decided what the eigenspaces are, and we found the simultaneous eigenstates of the operators. All this is standard machinery for Hamiltonians with symmetry. Now, however, there's an interesting physical fact, which is that in the case of the actual carbon-12 diatomic molecule, the states of odd angular momentum L equals 1, 3, 5, and so on, do not exist. The carbon-12 molecule only has even L's, L equals 0, 2, 4, and so on. The missing angular momentum states, so this is the diatomic molecule, it rotates, right? Just like that. So it's got some orbital angular momentum. The statement I'm making is the even values of L are not there. Excuse me, I said it wrong. The odd values of L are not there. The even values are present, the odd are not. So this is first of all an experimental fact. It's something that can be determined by spectroscopic data, and it also can be determined from thermodynamic data. It's just a fact about the carbon-12 molecule. This, in fact, is a special case of a general result which applies in systems of identical particles, which is called the symmetrization postulate. And I want to tell you what that is now. So you see how this particular exchange symmetry is different from parity. In the case of parity, we have both even and odd parity, and the Hamiltonian has both types of states. In the case of exchange, half of it is just missing. Okay, so the symmetrization postulate, I'll try to write it as briefly as I can. Symmetrization postulate. So in any system with identical particles, I'll abbreviate here, particles. The wave function psi is even or odd under exchange of identical bosons or fermions, even under exchange of bosons, identical bosons, and odd under exchange of identical fermions. Boson, as you know, is a particle whose spin is an integer, and a fermion is a particle whose spin is a half integer. In the case of the carbon-12 nucleus was spin 0, so that was the case of a boson. Electrons, of course, are examples of fermions. So the symmetry of the wave function is the exchange symmetry, the E12 eigenvalue. So the E12 commutes with the Hamiltonian. Therefore, the Hamiltonian possesses simultaneous eigenstates with E12. The statement is if you're exchanging even identical bosons, you're always in the even symmetry class. If you're exchanging identical fermions, you're always in the odd symmetry class. The opposite, the other symmetry classes don't exist. The symmetrization postulate is an additional postulate in addition to the measurement postulates that we dealt with last semester. It cannot be derived from those earlier postulates. In fact, it's an experimental fact, and that's how it was originally discovered. Nevertheless, you obviously on thinking about it, you'd like to say, is it possible to derive it somehow from more fundamental principles of some kind, even if it's not the measurement postulates that we studied already? And the answer is yes, this can be done, but only within the framework of relativistic quantum field theory. This was first carried out by Pauli in 1940 and amounts to what's called the spin and statistics theorem. The foundations of the spin and statistics theorem are the assumptions that relativistic causality holds, that signals can't travel faster than the speed of light, first of all, and secondly, that energies are bounded from below. We expect energies to be bounded from below because if they weren't, systems would make transitions, dropping down into lower and lower energy states, emitting more and more photons as the energy went down to minus infinity, and we'd see an infinite amount of energy released in the form of photons. Since we don't see that, we expect that all physical systems, the energies are bounded from below. Anyway, that's one of the ingredients in the spin and statistics theorem. Spin and statistics theorem is a big deal because it justifies this very important result from the physics of identical particles on the basis of quantum field theory. It's therefore regarded as one of the major accomplishments or triumphs of relativistic quantum field theory, that it's able to do this. Within the non-relativistic theory, which is the content of most of this course, you just have to take it as a postulate which is supported on experimental grounds. It is indeed experimentally verified. Now, once we've got the symmetrization postulate, we need to understand, we suddenly need to talk about, in our Hilbert spaces, we need to talk about the difference between the nominal Hilbert space and the physical Hilbert space. So for example, in the case of the carbon-14 molecule, there are wave functions which are antisymmetric under exchange. These are the ones with the odd values of L. You can write those wave functions down. Those are eigenfunctions of the Hamiltonian, as a mathematical problem. They just don't correspond to any physics. So the nominal Hilbert space has all the wave functions in it, regardless of the symmetrization postulates. The physical Hilbert space is a subspace in which the wave functions do satisfy the symmetrization postulate. What this means is that now it becomes possible to talk about wave functions which are not physical because they don't belong to the physical subspace. So I hope that's clear about this distinction between these two spaces. So now it becomes possible to talk about wave functions, which are non-physical because they don't belong to the physical subspace. An example would be an odd L rotational state for the carbon 12 C2 molecule. All right. In addition to non-physical wave functions, it's also possible to talk about non-physical operators. A non-physical operator A would be an operator A which would act on a state psi, which was physical, and produce and map it out of the non-physical subspace and produce a non-physical psi prime. If that were the case, if operator A did this, then we have to say the operator A is not a physical operator. Physical operators are ones that map the physical Hilbert space into itself. If an operator commutes with exchange, then it's automatically physical. It's easy to show that if it does so, that it maps any vector in the physical subspace into itself. It commutes with exchange, it's physical. So let's classify some things. If we took, for example, the position of particle 1, this is a non-physical operator because if I conjugate it with exchange, E12 dagger, it goes into X2. It doesn't go into itself. It's not invariant under exchange. This is a way of saying that X1 does not leave the physical subspace invariant. Now that's just the mathematics of it. The physics of it is the following. X1 is not physical because you can't measure the position of particle 1. What you can do is you can go to some region of space, draw some small region, and you can ask yourself whether there's a particle in that region. If you draw it small enough, it'll be only one particle most of the time. So you can ask yourself whether there's a particle in that region. And if there is a particle, that's fine, but you can't say whether it's particle 1 or particle 2 because they're identical. That's why X1 by itself is not a physical operator. On the other hand, the center of mass position is physical because when you conjugate it by exchange R12, it goes into itself. So that is a physical operator. All right, so this is now a distinction between both physical and non-physical states and physical and non-physical operators. Let's see. I think there was something else important I wanted to say, and I think it's escaping my mind right now. All right.
Excuse me, I'm sorry, I'm kind of confused on how like wide reaching what you've just said is. So you said that like you can determine with the mathematical formalism whether or not an operator is physical based on whether it goes into itself when conjugated by exchange. But
to be precise about it is if the operator commutes with exchange, then it's physical.
okay, but what if you had a system that isn't
See,
exclusively made up of
that's
identical
actually easy to show because the physical subspace is invariant under exchange. E12 just maps it into itself. Those are the states that are invariant under exchange. So if I have a state psi, and let's say psi is physical, so E12 psi is equal to psi. Now I want to know is a physical. So I want to know, does a psi belong to, does this belong to the physical subspace? That's the question mark, you see. Assuming that psi belongs to physical, does a psi belong to it? Well, to find out, we apply E12. But if E12 commutes with A, then this is A E12. And so that's a psi. So what this tells you is that a psi is invariant under E12 and therefore it's physical. So it's a simple proof, in other words, that if the operator commutes with exchange, then it is a physical operator.
Okay.
Okay, now go back to your question then.
I guess I was just confused because I can imagine a Hamiltonian, for example, which is an operator that describes particles that aren't identical.
Yes.
And so it would not commute with exchange, but it would still be a physical, it would describe a physical system, I would think.
Yeah, thank you for asking that, because now you remind me what it was I wanted to say a minute ago. This is an important thing. So this distinction between the physical and non-physical subspace only applies in the case of identical particles. Actually, the exchange operator, there's really no non-ugly way to define the exchange operator for particles that are not identical. Try it and you'll see. And
okay.
So we don't really have an exchange operator. But let's go to the case of this carbon 12 molecule. If we replace one of the carbon 12 in the diatomic with a different isotope, carbon 14, or if you wanted to choose a different atom that had spin 0 nucleus, you could do that. Change it to a different nucleus, in other words. Then the exchange operator is not so well defined anymore, and the transformations we use become more complicated because the masses are different and so on. Nevertheless, it is possible to talk about the angular momentum states of the rotor, the diatomic. There's no problem in that. And what you'll find is that if the two nuclei are not the same, then all of the rotational states, even and odd, they both exist. No question about it. It's well determined experimentally. It's only when the two nuclei are identical that, boom, half of them disappear. So that's the case where we need to distinguish between physical and non-physical subspaces. All right. So what I'd like to do now in the time that I've got left, I hope I can do it, is to move on to the case of the hydrogen molecule, H2. So what's different about the hydrogen molecule? Well, the potential energy is not that much different. Oh, well, first of all, let's start with the Hamiltonian. The Hamiltonian we had before was P1 squared over 2 plus P2 squared 2m plus P2 squared over 2m plus V of the distance between the two. And that was for carbon. Does this change for hydrogen? The main physics that changes in the case of hydrogen, that for what we're interested in tonight, is that the nuclear spin is now 1/2 because they're protons. This is ordinary hydrogen. The spin is a proton, has a spin 1/2. So the protons are fermions. So in contrast to the C2 molecule, the H2 molecule has atoms which are fermions, nuclei are fermions. Therefore, according to the symmetrization postulate, the total wave function should be antisymmetric under exchange. We're going to see what consequences that has. Now, you might say, if now the protons have spin, don't I need to change the Hamiltonian? Because after all, I've got two hydrogen atoms here, and there's two protons, and they've got two spins, and the spins have got magnetic moments pointing off in some directions. And there's an interaction, a dipole-dipole interaction between those two magnetic moments. So shouldn't there be extra terms in the Hamiltonian for the magnetic dipole interaction, right? The answer is yes, there are those terms in the Hamiltonian, but those terms are very, very, very small. These are really hyperfine effects, but even more than the hyperfine effects we considered last semester, which involved the proton interacting with an electron. That was a product of a nuclear magneton times a Bohr magneton. Here we've got the product of two nuclear magnetons. So the order of magnitude of the energy here is like 1,000 times smaller than what we saw in the hyperfine effects in the hydrogen atom last semester. This is a hydrogen molecule. Now, proton. So it's very, very small numerically. And this small contribution to the Hamiltonian has absolutely no effect on the argument that I'm going to make, which ends up giving you a very dramatic effect on the energy levels of the diatomic molecule ultimately due to the spin combined with the symmetrization postulate. So I'm going to ignore those spin dependent terms. They make no difference. So I'm going to be using the same Hamiltonian as I had for carbon. Well, the potential, of course, is different, but the potential does have qualitatively the same features as before. So it's the same shape of the curve. There are bound states in the same way as for carbon, and all that stuff I went through about approximating the energy levels also applies to hydrogen, at least down near the ground state, down near the bottom of the well, it does anyway. So that discussion doesn't change, nor for that matter does the transformation from lab coordinates of the two hydrogen atoms over to center of mass and relative coordinates. When we do that, we're going to get, of course, the Hamiltonian in those variables, which is going to be big P squared over 2 capital M plus lowercase p squared over twice mu plus V of R. It's the same Hamiltonian we had before. Now, what about the energy eigenfunctions? The psi then is going to be equal to, just like before, it's going to be a product of the center of mass part times the relative part. But we now have another part as well. We have a spin part because the Hamiltonian has spin. Excuse me, the particles have spin. Now, because of the fact that this Hamiltonian, neglecting those small terms I just neglected, because of the fact that this Hamiltonian does not involve the spin, it means that this spin contribution to the wave function can be anything. It can be any spin wave function, and it won't change the fact that this capital psi is an eigenfunction of H. So there's going to be degeneracies, you see, due to the possibilities of choosing different spin stuff. So one of the things we could choose here would be the spin state of the two magnetic quantum numbers M1 and M2. That'd be one possibility for the for the two hydrogen nuclei. Unfortunately, when I apply the exchange operator to this, we know what it's going to do to the phi, which is nothing. We know what it's going to do to the psi, which is bring out -1 to the L. But it doesn't do something nice to the M12. It maps it into M21, into a different state. And so what the result is, this psi, so written out this way, is actually not an eigenstate of E12. Now, E12 commutes with the Hamiltonian, so we know it's possible to find simultaneous eigenstates. It's just that this one that I wrote down is not such a simultaneous eigenstate. The way we find simultaneous eigenstates is we form linear combinations of degenerate eigenstates to make them into eigenstates of the new observable, in this case, E12. So we need to find linear combinations of M1, M2 to make eigenstates of E12. Well, this is actually easy. We do it by forming the singlet and triplet states, which are this natural thing to do when you're combining two spins. So I'll write these as S and M like this, where S is either equal to 0 or 1. The 0, of course, is the singlet, and the 1 is the triplet. And by now, I hope you've all first year, really all undergraduates taking quantum mechanics should have memorized by now the Clebsch-Gordan coefficients. Anyway, here's how it works out. Is if I take the singlet state at 0, 0 is 1 over root 2 times 1/2 minus 1/2 minus 1/2 times 1/2. I hope the notation is clear here. 1, 1 for the triplet state is going to be equal to 1/2 times 1/2. 1, 0 for the triplet state is going to be equal to 1 over root 2 times 1/2 minus 1/2 plus minus 1/2, 1/2. I'm just, if you like, I'm just looking up Clebsch-Gordan coefficients in the tables, and this is equal to minus 1/2 times minus 1/2. The first one is the singlet, and the remaining 3 are the triplet states, called for obvious reasons for the number of states involved, number of magnetic quantum numbers. Now, one of the things you can see by looking at the expansions here is that under exchange E12, the singlet states are odd, comes in with a factor of -1. That's because the minus sign here. Whereas all 3 triplet states are even, they're even under exchange, E12. So let's write this way, is that E12 applied to S and M is equal to what I'll call sigma sub S times S and M, where sigma sub S is equal to -1 when S is equal to 0, that's the singlet states, and +1 when S is equal to 1, that's the triplet states. In other words, organizing the spin states by the quantum numbers of total S squared and SE automatically gives us eigenstates of exchange. And the eigenstate, the eigenvalue of exchange depends only on the S quantum number and not on the magnetic quantum number. All right, now then. By the way, the fact that the M1 and M2 didn't work is due to the fact that S sub Z sub 1 and S sub Z sub 2, which are the Z components of spin of the two particles, of which the M1 and M2 are the quantum numbers. S sub Z sub 1 and S sub Z sub 2 are not physical operators because they label the atom in question, they label the particle in question. Any operator that labels the particles is not, in other words, is not invariant under a permutation of labels, is not physical. This is the same issue that I had earlier with the positions of the two particles, X1 and X2. However, forming eigenstates of S squared and S sub Z, those operators, you look at the formulas for them, you'll see they do commute with exchange. And that's just what we're getting here. So what we want to do is take these spin states and replace them by S and M like this, where there are the four possibilities of S and M. And if we do this, then what we find is that E12 acting on the energy eigenstate psi like this, which is E12 acting on first the center of mass part times the relative part, which is NLM, times now the spin part SM, like so, gives us a phase factor, which is nothing from the phi, -1 to the L coming from the relative wave function, and then this quantity sigma sub S coming from the spin part, where the sigma sub S is defined over here. It's +1, -1, depending on the value of the spin. And this is then multiplying onto psi. So now, by the symmetrization postulate, this tells us that -1 to the L times sigma sub S must equal to -1. -1 because the protons are fermions. They have to be antisymmetric under exchange. And this, as you see, then gives us a linkage between the orbital angular momentum L and the spin angular and the spin quantum number S. In fact, we can arrange this in a table here. Let's write this way. Let's write singlet and triplet. Let's write out the possibilities. Singlet and triplet. So they have the spin value is 0 for singlet and it's 1 for triplet. Let me make a table. The degeneracy, by which I mean the number of magnetic quantum numbers, is 1 for singlet and 3 for triplet. Of course, that's where the name comes from. Now then, what is the sigma sub s? The sigma sub s is -1 for singlet and +1 for triplet. So that means that -1 to the L has to be opposite. It has to be +1 for singlet and -1 for L. So that the overall exchange symmetry, and we call it E12, is -1, -1, as required by the symmetrization postulate. And so what does this tell us about the value of L? L must be even for the singlet states, and it must be odd for the triplet states. I'm actually out of time, so let me just mention one more thing. So the even states are called para states, and the odd states are called ortho states. I'll come back to that at the beginning of the lecture next time. But in any case, the result is that for the hydrogen H2 molecule, you can see that both angular momentum states, both even and odd, are allowed. This is unlike the carbon case where only the even ones were allowed. Both even and odd are allowed, but they have different degeneracies. The spin degeneracy is 3 times as much for the odd states as it is for the even states. Now, what that means is that, for example, at high temperatures, when the occupations of the various energy levels is just proportional to the degeneracy, it means you're 3 times as likely to have L equals odd as you are to have L equals even. At high temperatures, the quantum number L is likely to be large. So let's say between L equals 15 and L equals 16, there's going to be 3 times as many L equals 15s states as there are L equals 16. So this is the impact that the symmetrization postulate has on, and now I'm speaking of the thermodynamics of the H2 molecule. Okay, so I'm sorry I went over too much, but I wanted to finish this table here. This is this then shows you the impact of the symmetrization postulate on the rotational and vibrational state. This doesn't affect the vibrational states. The rotational states of homonuclear diatomic molecules such as carbon-12 and hydrogen. Okay, so that's all for tonight. Are there any questions about this?
Yeah, what is lowercase e12?
Lowercase e12 is supposed to be the eigenvalue of capital E12, so it's got to be +1 or -1. But the point is the symmetrization postulate demands that it be -1 for the physical subspace.
All right, thanks.
Okay, any other questions? The physical subspace is the one in which lowercase e12 is equal to -1. The non-physical space is complementary to that with the other eigenvalue. All right, good. Yes, question.
So when you were first defining the exchange operator,
Yes.
you define it as the tensor product for like one state or one like alpha spans the Hilbert space for a single particle and beta spans the Hilbert space for the other particle.
Yes.
And then you took the tensor product.
Yes.
And then E12 is alpha beta, or E12 on alpha beta is beta alpha.
That's right.
Why? So it seems before that the order, like alpha or beta, did not matter for distinguishable particles. So why does that order matter here?
The order does matter. If I had, for example, let's say I had 2 electrons in, let's see, you want distinguishable particles, don't you?
I guess all I mean really is like if we have like
it's the
NLM as our basis, it doesn't really matter if we put L first or N first.
No, but in NLM are the quantum numbers of just a single particle. So if you want 2 particles, you've got 2 sets of NLMs, you see. So one particle is like, 1s and the other one's 2p or something. They're different states, you see.
Okay.
Yeah, so the exchange operator only acts on the 2 particle Hilbert space. So it doesn't make any sense to say what E12 does to alpha, because that's just a single particle vector. But we
Mhm.
form basis vectors in the two particle Hilbert space by multiplying basis vectors from the single particle Hilbert space. So that's where the alpha times beta comes from. And the E12 does act on that. In fact, we defined E12 in terms of its action on alpha product beta.
Okay,
We can't exchange two particles if there's only one particle.
thanks.
Okay, good. Any other questions?
I actually wanted to continue off of that because you just made a link between the spin state of the particle and the symmetrization postulate. So can't we say something about how it's going to interact under exchange if it has a certain spin, but it's not in a two particle system, or is that just not intrinsic to a single particle?
Well, you can't exchange particles if it's not a two particle system.
Yeah, sure, but we can assume how it might behave if we were to introduce it to a two particle system. So that symmetry of the exchange isn't intrinsic to any single particle. Where does it come from when we construct that Hilbert space?
I mean, when we construct the Hilbert space for a two particle system, where did exchange come from?
Yeah, like we can tell intrinsically the anti-symmetry or the symmetric exchange from that spin statistic. So is there like a way to write the in the tensor space that extra symmetry, not just a tensor product of the two particles?
I'm not sure I understand your question, but sometimes we talk about a system with a single electron. Maybe I'm not answering your question, but I mean, we frequently talk about a system with a single electron, like in hydrogen. Of course, the universe is full of other electrons. So why aren't they part of our system? Well, part of the reason is because we assume that they're not interacting, and we've made measurements so that we've got a quantum system, with pure state. We can talk, if we make enough measurements, we can get it into a pure state, with a single particle. That's certainly true. And then we proceed to ignore the rest of the electrons. Now, you might well ask, since there is another electron somewhere, this is like Hal in the movie 2001, there's another one. Okay, there's another electron somewhere. If we included that, even if it's not interacting, maybe it's just sitting over in San Francisco, we still have a two particle system, right? And so that system must obey the symmetrization postulate. It has to be true that it does. So the question is, if we take that into account, does it mess up the simple-minded description that we were making a minute ago and trying to ignore that other electron? And the answer is no, it doesn't. You can work through the details of it, and you'll find that it's okay to be dealing to analyze our single electron system and ignore that other one, as long as it's not interacting with it. And you won't get anything wrong by doing that. But this is part of the way of exploring, the logical consequences of this formalism that we're introducing here. Now, I don't know if that answers your question at all, but that is a part of this whole story. I mean, if you're willing to accept that we can talk about single particle systems, then for them, exchange just simply isn't defined. If we bring that electron from San Francisco over, and it does start to interact, and you might want to do that, then you do need to talk about the exchange operator for both particles. This gets into the issues of entanglement and so on when you talk about multi-particle systems. Are they just tensor products of, tensor products of separate wave functions, or are they entangled? If I didn't answer your question, I don't think I did. Maybe you want to ask it again or rephrase it.
I think I will email you about it. I need to formulate it better.
Okay, good. In the meantime, take a look at the notes and see if that helps explain it better than I did. Are there any other questions?
Yeah, I'm a bit confused about something. So I thought the symmetrization postulate said that like systems of fermions needed to have wave functions that are anti-symmetric under exchange.
Yes.
But you made a comment right at the end of the lecture about the statistics of hydrogen, which I think the hydrogen nucleus is a fermion at high, sorry, I might be confusing myself, at higher temperatures where you would have like 3 times as many odd or even angular momentum states as odd. Why would you be able to have both? Wouldn't one of them be outlawed by the symmetrization postulate, or no?
No, that's what you see here. You see, it's because to achieve the overall, to achieve the overall requirement that the system be odd under exchange, that's what these two -1s mean. We've accomplished it by making either the spin part antisymmetric and the spatial part symmetric, or vice versa. That's what's happened here.
Oh, okay.
So-
I
so
think I
both-
was confusing a model that doesn't consider the spatial part. Okay,
Yeah, no, we need to do that. So, I mean, in the molecule, you have to remember the spatial part was all there was for the carbon.
sure. Okay,
And
okay.
and that led to the rule that only even L exist. But in the case of hydrogen, both even and odd L both exist. But that doesn't mean that the symmetrization didn't do anything, because the degeneracies are different. So in fact, there are 3 times at high enough temperatures, there's 3 times as many odd L states as there are even states.
Okay, great. Yeah, that's clear. Thanks.
High enough temperature means that you can sort of gloss over the energy difference between the L and L+1. I mean, there's a Boltzmann factor that determines the populations of the L and L+1, but the Boltzmann factor also has a degeneracy in there too. So if the energies are nearly equal, the Boltzmann factors are nearly equal, but the degeneracy factors are 3 to 1.
Perfect. Thank you.
Okay, good. Any other questions? These are great questions, by the way. Okay, if there's no other questions, I shall stop screen share, and then I shall stop recording. Thank you so much for reminding me to start recording. I'm glad we did that.